So for number one question, explain how conservation of linear momentum applies to handball bouncing off a wall, right? So if you think about handball bouncing off a wall, think about like Earth as giant mass, and this wall is sticking up from Earth, so it's attached to the Earth, basically. Okay. So as the handball comes in to the wall, it has initial positive velocity. Okay. And then after it bounces off, right, most likely it's not going to be, it's going to lose some energy. Okay. So it's going to have a negative MV final. Okay. So if you were to think about how this, two ball and the wall system works out, right? Because there's no external force, right? Since there's no external force acting on the system, a ball wall system, right? The change in momentum must equal to zero. Okay? That means sum of all momentum initial must equal to sum of all momentum final. Okay? So if we were to look at this ball wall system, all the initial momentum I have basically the momentum of a ball, which is mvi, plus the mass of the wall, which is attached to the earth, right? So mass of wall attached to earth, right? Times v initial, right? Of wall. This is ball. Must equal to the mass times the velocity final of the ball plus the mass, I should put this, times mass of the wall, right, times the velocity final of the wall. Well, initially, right, the wall is at rest, right? So this whole term goes to zero. So here, if I were to put in, right, the values here, MVI must equal to, right, M times negative VF, right, plus the mass of the wall, which is pretty much the mass of the Earth because it's attached to the Earth, times the velocity of the wall recoiling. But this is really, 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 really small because this is same thing as the mass of the Earth. So can you imagine how small this has to be, right? So so it does recoil. I mean, after the ball hits it, but it's just going to be so small. It's not even like coming into a factor. Okay, so that's what's going to happen. So when this happens, this is going to be just ridiculously small. Because if I bring this to the other side, this becomes positive, And then if I divide by the mass of the Earth, which is like 6 times 10 to the 24th kilograms, 10 to the 24th, when you divide whatever this is by that, it's just going to be ridiculously small. All right? All right. Next. It is said that during 30 miles per hour collision, a 10-pound child can exert 300 pounds of force against the parent's grip. How can such a large force come about? Yeah, old days, you know, people used to actually not wear seatbelts. And if they did, they would actually wear like a lap belt only. And after, like, lovely couple have a baby at the hospital, on the way back home, the mom would actually hold the baby in her arms, and dad would be like very proud and be like looking at the baby instead of the road. And when they get into a car crash at only 30 miles per hour, this child's going to be a projectile inside a car. Okay. Unfortunate incidents happen many times. So, since if we were to look at how force is equal to the change in momentum over change in time, in an accident, right? In an accident, this delta t is very, very small in collisions. Okay? So when you divide, mv final minus mv initial by a very, very, very small delta t, right? Your final obviously is going to go to zero because when you crush the car, it's going to go to zero. Here, we're going to have mass times the initial velocity in miles per hour. Now you could convert this obviously to feet per second, right? And you could convert this 300 pounds into, or 10 pounds into mass by dividing it by 32. Then you'd be slugs, okay? But that's not the important thing. The important thing is that understanding that whatever this is, which is just a number, dividing by the negative number divided by a very, very small number, like 0.00002 seconds, then the force spikes huge, huge. So this concept is more important than just numbers. Okay? So understand this first. Because if you want to see the numbers, 10 pounds is equal to, right, mass times the acceleration due to gravity, which is mass times 32 feet per second squared. So the mass of the baby is 10 divided by 32, which is approximately 0.3125 slugs. I'm not saying baby is a slug, but that's how they measure mass in British system. Okay. Also, 30 miles per hour is equal to, right? Well, same thing. 30 miles per hour, which is in 1 mile, right? There are 5,280 feet. And in 1 hour, there are 3,600 seconds. So if you convert that, you're going to get 44 feet per second. So if you plug all these values in here, and then you divide that by this, right? It's going to be ridiculous, okay? So let's find out how much time it takes. So since your VF is equal to 0, your VI is 44, right? Um, your force a baby will experience is 300 pounds, right? And we could calculate the time now because we know the mass. Mass is equal to 0.3125. So if we were to look at this formula right here, let's calculate the time. Now, this is only for an example, okay? So this is not the proper time. So force is equal to mv final minus mv initial over delta t. So 300 is equal to, here, your final velocity is going to be 0. So this whole thing is going to go to 0. So 0 minus 0.3125 times 44. Divide that by delta t. So your delta t is equal to, right, I guess, whatever this is, right, which is 44 times 0.3125 is 13.75. Divide that by 300. So it's going to take actually around 0.0458 seconds for the accident to happen. So instead of this, if we were to supply this onto that, that's why the baby will feel, okay, 300 pounds of force against the dashboard or the windshield. All right. So that's why I guess we start bringing in baby carriages and safety car seats and all that. It's very important. So yeah, so many unfortunate incidents happened before. All right, next. Okay, now we have a 95, not 35, 95 kilogram athlete is running at 4.2 meters per second. What impulse will stop him? Okay, well, impulse is equal to change in momentum. And that change in momentum is also equal to force times delta t. They're both the same things. But this is the most important one, change in momentum. So since change in momentum is momentum final minus the momentum initial, we can find impulse by finding, well, final momentum is mvf minus mv initial. Well, final momentum is 0 because your final velocity is 0. So 0 minus 95 times 4.2. So you get negative 399 kilograms meters per second as your impulse. Or you can simply say negative 399 Newton seconds is also the same thing. Okay? All right. Any questions so far? All right then. Number 7. Until he was in his 70s, Henry Lamoff, right, excited audience by belly flopping from a height of 40 feet into 12 inches of water, assuming that he stops just as he reaches the bottom of the water. Okay, what is the average force on him from the water, assuming his weight is 160 pounds. Why are we using all this British system? I don't know. Okay, so let's find out what's going on. His mass is 5 slugs because 160 pounds divided by 32 feet per second squared is just 5 slugs. Okay. Now he's going to be starting here. He's going to fall straight down, and right before he hits the water, I want to know what his velocity is. Okay. Because his velocity right before he hits the water, we can figure that out. So what is the velocity? Well, we know you can use, um, conservation of energy here if you want to, right? You could say total energy here is equal to total energy here, right? Um, yeah, I guess before. All right. Well, you could do it so many different ways. Okay. So right before he hits the water, right? Right before he hits the water, let's find out how fast he's moving. Okay. Here, VF squared is equal to VI squared plus 2A delta Y. So here, the final velocity, which is this, which is V hit, before he hits the water, right? And initial velocity is 0 because he just like sort of falls off the ledge, plus 2 times acceleration happens to be 32 feet per second squared. And delta y is 40 feet. Now you could put negative here, and negative will cancel out anyway. So we should know that already. So velocity right before it hits the water comes out to something like 50.6 feet per second. Like I said, I don't know why we're using empirical British. Now we know that. Now we're going to say this V hit is now initial condition, and this becomes now our new final condition. Okay, so here was the initial for phase 1 and final for phase 1. That final for phase 1 is now the initial of phase 2. Okay, so here, what is the deceleration of this man as he slows down from 50.6 feet per second to 0 feet per second at final? All right, so we're going to find the deceleration of this guy, belly flopper, right? So here, VF squared is equal to VI squared plus 2A delta Y. Here, final velocity is going to be 0 now because at the bottom of the pool, it's going to stop. That is equal to initial, which is now 50.6, you have to square that, plus 2 times 8 times delta y is just 1 foot. Now again, delta y, measuring from here to here, should be negative. Okay. So when you solve for the acceleration, your acceleration is equal to, if you use your calculator correctly, you should get something around 1280 feet per second squared. That's how, and it should come out to be negative. Okay, it should come out to be negative. No, actually positive, because acceleration has to go up direction. So when we have this acceleration, right, now we can use how much time it's going to take for this man to come down to a stop. So we can use VF is equal to VI plus AT. Then VF 0, VI 50.6 plus acceleration, right, is 1280. Again, I'm sorry, VI is negative 50.6 because it's coming down, times T. So the time is going to be 0.0395 seconds in 1 foot of water, 1 foot distance. Okay, so it's going to take this much time to travel 1 foot to make him come to stop. Now that we know that, here we can say force is equal to delta P over delta T. We're looking for force, and that is mv final minus mv initial over, right, delta T, which we calculated. V final is going to be 0. So negative 5 slugs times negative 50.6 feet per second. Divide that by 0.0395 seconds. So that is equal to 6,400 pounds. So how much? I mean, if, that sounds like, oh my God, okay, that's pretty big. But how much compared to his weight, right? That's about 40 times his weight. That's ridiculous. It's a miracle that he actually survives. Can you imagine 40 of you on top of you, laying on top of you? You will be able to survive, right? And imagine not only that, it's dropped on you, right? For this many seconds from 1 foot above. It's going to be bone crushing, right? So it's amazing how he actually survives. There's some actually like video footages. If you could Google it, you could see him actually do this. It's pretty intense. It's like short, bold guy, He's got a belly and a beer belly, and he just does it. It's amazing. All right, all right. Moving on. A golfer hits a golf ball, right, giving it an initial velocity of 50 meters per second, 30 degrees above the horizontal. Right? So this is important. Assume that the mass of the ball is 46 grams. So the mass is equal to 0. Right, 0.046 kilograms. Make sure you have everything right. And the club and ball are in contact for 1.7 milliseconds. So delta T is equal to 1.7 times 10 to the negative third seconds. Okay. A, what is the impulse of the ball? Right. So for part A, impulse is equal to change in momentum, or is also equal to F times delta T. Right. Well, we know the ball has usually when you play golf, The ball is at rest when you hit the ball. It's on top of a tee. Okay, even that is so hard. You're not even hitting a moving ball. You're hitting like a stationary ball. It's still tough. So the impulse is equal to momentum final minus the momentum initial, which is mv final minus mv initial. All right. Now, initially, the ball is at rest, so it goes to zero. However, the mass of the ball, which is 0.046 kilograms times 50 meters per second, is equal to 2.3 kilograms meters per second. And this will have direction, which is theta is equal to 30 degrees. And it's important to have that direction as part of the impulse because it is a vector. Okay? So impulse is equal to 2.3 kilograms meters per second, 30 degrees. Okay? So what about part B? Impulse on the club. Well, it has to have exact same amount in the opposite direction. Okay? So therefore, it has to be 2.3 kilograms meters per second. Theta has to be 180 plus this, which is 210, right? Well, if it has to be in the opposite direction, if this is 30, it has to go in the opposite direction. So if you add 180 to this 30, you're going to get 210. Okay? What about part C? The average force exerted on the ball by the club. Well, average force is equal to delta P over delta T. And since we know the delta P, which is 2.3 kilograms meters per second, divide that by delta T, which is 1.7 times 10 to the negative third seconds, and we get ourselves 1353 newtons. Because kilograms meters per second squared is basically newtons. And it has to be at angle of 30 degrees. Because force, again, is a vector, so you have to have direction. And then for part D, right, D says work done on the ball. How much work is done on the ball? Well, work done is equal to change in kinetic energy, which is kinetic energy final minus the kinetic energy initial. Initially, the ball's at rest, so 0, right? So 1/2 mv final squared is what? the work done is. Therefore, 1/2 times the mass, which is 0.046 kilograms, times initial velocity is 50. Square that, and you should get 57.5 joules of work done. Okay. Yeah, let's go fire some machine guns. It fires 50-gram bullets at speed of 1,000 meters per second. I think we did this problem already in our notebook, in our notes. Okay. So the gunner holds the machine gun in his hand and exerts an average force of 180 newtons. So force average is equal to 180 newtons, right? And the velocity of the gun is 1,000 meters per second. Okay. So force is equal to, right, delta P over delta T. But if we have n number of bullets, right? So we can say the n number of bullets per unit of time, so n over delta T, right, is equal to number of bullets per second, right? It's the rate of fire, right? Therefore, right, my force is equal to n times, right, mv final minus mv initial over delta t. Okay. So if we were to find out, okay, 1 minute is delta t. Good. Okay. So delta t is 60 seconds. So let's see. He could only hold on for 180 newtons of force. So let's find out how many bullets he can shoot. So final velocity is 0.05 times final velocity of the bullet is 1,000. Initial velocity for the bullet is 0, so minus 0, over 60 seconds. All right. So if we multiply 60 times 180, divide that by whatever this is, 1,000 times 0.5, right? 50, right, is equal to n. Therefore, 180 times 60 divided by 50, we get 216 bullets per minute. All right, because if it goes any more than that, he would lose control of the gun, which just won't have enough force to hold on to it. All right. All right. '21. This can get a little tricky here. So let's take a look at this. Um, in figure 10-30 shows an approximate plot of force versus time during a collision of 58-gram tennis ball with the wall. Okay, so let's say you're like shooting this tennis ball against the wall. So your V initial is, let's say, negative V, and the ball bounces off and comes out this way. Your V final is equal to V, and V is 34, right, meters per second. So this is what's happening. So what is change in momentum, right? So impulse J is equal to change in momentum, which is equal to, right, integral of F dot delta T, or dt, since we're integrating, right, which is equal to mvf minus mv initial. Here's this. Integration basically is simply area, okay? So if we find the area of this, we get our delta P, okay? So my delta P is equal to, right, here, 2mv is what we have, okay? So, um, because we have m times v final, which is positive, so here, I guess mass is equal to 0.058 times v final, which is positive 34, minus 0.058 times vi is negative 34, okay? So what is my change in momentum? So here, I guess if you do this, 0.058 times 34, if you multiply that by 2, you're going to get 3.944, okay? All right? So the milliseconds, yeah, this is kind of messed up. Yeah? Well, I just made the ball going this way, in the negative x direction. Yeah, I could have made it go that way and this would have come out negative, but I just made it go in this way first in the negative direction and bounces off out in the positive direction. Yeah, it's okay. Yeah. but it still should work out the same. The value should still come out to be the same, but except you'll just be negative, right? All right, so um, here, if we were to find this time right here, so if you were to sort of bring this area to this time, we're going to get this time to be 4 milliseconds, right? So to find the delta P of this, okay, what is all this delta P? This area is what we're going to try to find. So this now can be equal to, right, F max times delta T. So if I put delta T to be, let's say, 6 times 10 to the negative third seconds, right, we can solve for F max. But because this F max does not happen constantly, I got to find out when this would happen if I bring this to here, right? So bringing this to here to find my constant F max, I have to limit it to 4 milliseconds instead of 6 milliseconds to make this F max constant. And that's the tricky part of this. Because this F max does not happen for this many seconds, 0.6 milliseconds. It only happens so that it manipulated so we could get that 4 milliseconds of time of contact to make your F max constant. So we will use this delta T in here instead of 6 milliseconds. Therefore, 3.944 is equal to F max times 4 times 10 to the negative third seconds. So your F max is equal to 3.944 divided by 4 AE negative third. And that's how you get 986 newtons of force. Yeah, this, a lot of times kids will use this, but you cannot do that because then your F max is not this. You're finding the average force then if you're using this time. If you're looking for the max, you have to manipulate this equation so your force max becomes constant. So that's the difference why we use this delta T rather than 6 milliseconds. Because this 6 milliseconds will give you an average force somewhere around here. Okay? That was tricky. Not too many people would have gotten that. All right, 23. So for this one, we have 300 gram ball with speed of 6 meters per second, strikes the wall at an angle of 30 degrees, then rebounds the same. So this angle is 30 degrees. And this angle is also 30 degrees. Okay? So this ball coming in at 6 meters per second will have VIX and VIY. Okay? So if you were to calculate this V, I guess you could think of it, here's your initial velocity. And you can say this is your VIX and this is your VIY. And then here's your final velocity. And I guess this angle here is 30 degrees. And this will be your VFY. And this is the angle 30 degrees. And this is your VFX. Yeah, this question is usually asked on some form like this on AP tests. Okay, and a lot of kids get tricked out on this. So if you were to look at this and say A, it is in contact for 10 milliseconds, so that's good to know. Delta T is equal to 10 times 10 to the negative third seconds. What was the impulse on the ball? For the impulse on the ball, you have to look at both x and the y. Okay, so you have to look at change in momentum in x is equal to momentum x final minus the momentum x initial. Okay, there's only one ball, so you only need to do one at a time. So m times VFX minus m times VIX. Therefore, here, your mass is 300, so 0.3 kilograms, times VFX is 6 times sine of 30 degrees. Are we okay with that? Because this is 6. That will give you what? That will give you 3. And, oops, sorry, this is negative 3, sorry, negative 3, because F. The initial, right, is going this way, it's positive. F is going negative for the X. Minus 0.300 times, initial is positive 3. Therefore, the change in momentum in the x direction is actually negative twice as much as this, right? So 2 times like 0.9 or negative 1.8 kilograms meters per second x hat. But what about the y's? For the y's, the change in momentum for y's is equal to the momentum y final minus the momentum y initial. Again, since we only have one ball, we just need to just do one at a time. So here, there is no change in momentum in y because this one's going up and this one's going up, so they're both positives, where this one was positive and this one was negative. So there was change in the x direction, but there's no change in the y direction. So m times v fy minus m times viy. Here, what is cosine of 30 times 6? So 6 times cosine of 30 is 5.2. So this is 5.2 meters per second. So is this, right? This is 5.2 meters per second, and they're both positives. Therefore, here 0.300 times positive 5.2 minus 0.300 times positive 5.2. So you'll get a 0. This minus that will give you 0. Where in the x direction, you get double the initial. All right. So this is the only one that survives. So change in momentum in y is 0. Okay. So what's the total? What's the total impulse? Total impulse is equal to just negative 1.8 kilograms meters per second exit. And then you could, if you want, you could put plus 0 y hat if you want to. That's okay. All right, then what about part B? Part B asks, all right, how much average force was exerted? Well, we know F is equal to delta P over delta T. We already know, right, how much change in momentum we have, negative 1.8, right, kilograms meters per second exit. Divide that by 10 milliseconds. So my force comes out to, I guess, negative 180 newtons exit. Okay? And that makes sense because force has to be acting this way to change that ball's momentum. It has to act in the negative x direction. So that makes perfect sense. All right. Next. All right. Yeah, you should like have this like, written down somewhere on your calculator, or like even program this in your calculator so you don't have to re-derive this. This is going to save you a lot of time if you memorize it, or if you actually have it programmed in your calculator, or just, you know, have it somewhere convenient. Okay? Have it somewhere convenient so you can always take it out. Okay? And this only works for elastic collisions. Okay? In one dimension. You cannot use this in any other situation, right? And this only works also at when M2 is at rest, okay? So so this is a very, very special case, okay? You cannot use these anywhere you want. It only works if it's elastic collision, if they're head-on collision in one dimension, okay? All right, so 34, if I had a body of 2 kilogram mass, makes an elastic collision with another body at rest, and continues to move in the original direction, but with only 1/4 of the original speed. Okay, so it looks like we're looking for which one? V1, right? What is the mass of the struck body? So here we can use this one because we know a lot of information about your V1 final and you know your V1 initial. Okay, so V1 final is equal to M1 minus M2 over M1 plus M2 times V1 initial. Okay, so here your V1 final happens to be 1/4 your original V, right? And that is equal to M1, which happens to be what? 2 kilograms, right? Minus M2, whole thing over 2 plus M2, V1. This V1 and this V1 can cancel out. Therefore, if I multiply this 2 plus M2 whole thing over 4 is equal to 2 minus M2. I mean, you know how to solve the rest, right? Come on. So this is like 2 plus M2 plus 8 minus 4M2, right? So you get 5M2, 5M2 is equal to 6, right? Is that right? Check my math. So what's my M2? My M2 is equal to 6 over 5, which is 1.2 kilograms. All right, that was silly. That was easy. Let's just plug and chug. Okay. All right. Now let's take a look at some more difficult ones coming up. Okay. Okay, this one's kind of this one's hard for these. All right. Let's take a look at the next one. Again, this is a head-on collision. Okay, a steel ball of mass half a kilogram is fastened to a cord, and you got 70 centimeter long, and it's fixed at a far end, and it's released when the cord is horizontal. At the bottom of the path, the ball strikes a 2.5 kilogram steel block initially at rest. So again, it's elastic collision, head-on collision. Right? The collision is elastic. Find A, the speed of the ball, and the speed of the block both after the collision. Okay, so you have to find out how fast this thing is coming down. So you should really try to find what the initial velocity is, right? First. So for that, you can use total energy initial is equal to total energy final. Initially, I only have potential energy initial. Final, I have kinetic energy final, right? So initial mgh is equal to 1/2 mv squared. So notice the masses cancel out, and my V is equal to square root of 2GH, right? Which is equal to square root of 2 times 9.8 times 0.7. And if you work that out, I think you'll get 3.7 meters per second. That is your initial velocity, right? So now that we know that, right, that is this, okay? So we're looking for V1 final, which is the ball, right? So V1 final is equal to M1 minus M2 over M1 plus M2 times V1 initial. So if we plug that values in, V1 final is equal to then M1, which is 0.5 minus 2.5 over 2.5 plus 0.5, right? Times 3.7. So if you work it out, you're going to get negative 2.47 meters per second. So it's going to rebound backwards, right? It's going to bounce back. Now let's find what is the velocity of 2. So my V2 final is equal to 2m1 over m1 plus m2 times v1 initial. So my v2 final is equal to 2 times 0.50 over 3 times 3.7, right? And that, if you work it out, comes out to 1.23 meters per second, and it's positive. So after they collide, they're gonna go, like, like that. Okay. Alrighty. 36. A platform scale is calibrated to indicate the mass in kilograms of an object placed on it. So it's basically a digital scale, really, right? Um, Particles fall from a height of 3.5 meters and collides with the balance pan of a scale. The collisions are elastic, and the particle rebounds upward with the same speed they had before hitting the pan. If each particle has mass of 110 grams and collision occurs at rate of 42 per second, what is the average scale reading? Okay, so we have to find out, first of all, what is the speed that it comes down when it's basically dropped from 30.5 meters height, right? So again, the total energy initial is equal to total energy final for this ball hitting here. So here is just mgh is equal to 1/2 mv squared, right? So we can cancel out the masses and find this v right before it hits, okay? So my v is equal to square root of 2gh again, right? So v is equal to square root of 2 times 9.8 times 3.5. So what is my v? I think you get something like 8.28 meters per second. Therefore, this is sort of like a machine gun, right, problem. So the rate is equal to, right, 42 particles per second, right? Same thing as 42 bullets per second. Same thing. We use N for the bullets and we're going to use R. Okay? And the mass of each bullet is 0.11 kilograms. So the force is equal to R, right, times delta P over delta T, right? So this basically turns into, I'm sorry, maybe N, sorry, N. Therefore, since this is turning into, right, whatever this R is times delta P, which is just R times MV final minus MV initial. Now remember, your final is going to be positive velocity because it's going to bounce up. Your initial is going to be negative velocity on the way down. Okay? It's not quite drawn. It should be like coming straight down and bouncing straight up, really. You know? So it's not drawn quite the way it should have been. Okay? So if you were to think about 42 times 0.11 times final velocity is up going this way, right? Which is positive 8.28 minus 0.11 times initial velocity is on the way down, so it's negative 8.28. So if you work this thing out, you're going to get 76.5 newtons. All right. Now let's talk about some meteors. A meteor crater in Arizona. If you ever drove there, it's like pretty cool. It's such a circular, perfect circle. It's thought to have been formed by impact of a meteor with Earth some 20,000 years ago. The mass of the meteor is estimated to be 5 times 10 to the 10th kilograms. That's pretty heavy. And its speed was 7,200 meters per second. So they're giving us all these. And if I see someone using 20,000 years for delta T, I'm going to have to hit you. What speed would such a meteor impart to Earth in a head-on collision? Right? Now, this is not an elastic collision. Right? What's happening is the Earth is absorbing the meteor. Okay? We're not going to worry about all the debris flying up. Okay? We're not going to really worry about like all the ejections from the impact. But we're just going to look at the instant when the meteor is absorbed by the Earth. So it becomes a completely inelastic collision. So sum of all momentum initial must equal to sum of all momentum final. Initially, I only have, the meteor moving, right? M meteor times V meteor initial, right? After the collision, I'm going to have the mass of the meteor plus the mass of the Earth. They become one and move off at a final common velocity. Right? So here, the mass of the meteor was 5 times 10 to the 10th kilograms times 7,200 meters per second is equal to, right, 5 times 10 to the 10th plus 6 times 10 to the 24th. So when you add these together, what are you going to get? Well, it's just going to be this, because this is 10 to the 10th. So it's going to be like way over here, like 6.000000000000005, right, times 10 to the 24th. So that's not going to make that much difference, right? When I add this, it just becomes 6 times 10 to the 24th. This is just like a rounding error, basically, the meteor. All right. So what is it then? So here, if we do, you know, 5 EE 10 times 7,200 divided by, that's like 3.6 times 10 to the 14th, right? Divide that by 6 EE 0.4, you're going to get VF is equal to 6 times 10 to the negative 11th meters per second. So this tells us the Earth is really, really, really big, really massive. It's not going to get affected that much at all, right? So is it affect or effect? I don't know this. Is it affect AFF or is it EFF? Come on, who was the English major here? All right, let me know about that. All right, got 2 minutes. I'm gonna stop for today. I'm burnt out. You guys are probably too. Please continue on. I'm gonna try to finish up the rest of the homework packet, I guess on Thursday when we meet. All right, and then we'll have tests on this 9 and 10 on, but during the weekend, I guess. Okay, during the weekend. I think it's going to be mostly multiple choice. There's some free responses, but it's a short answer free responses. So the answer could be also multiple choice. So we'll see. We have to show work. All right. Good. Any questions?
Thank you, Mr. Kim.
All right. Have a wonderful day, everybody.
Thank you.
And see you Thursday.
Thank you.
Okay.
Thank you.